Hi, I'm Quinn, and today we're diving into quantum algorithms. Quantum computers are often described as faster, but that slogan hides a crucial truth. They're not faster at everything. They're faster at specific kinds of problems that have the right structure. Here's the intuition. Quantum algorithms use interference to amplify correct answers and cancel wrong ones. If a problem has a pattern that interference can exploit, quantum computers can win. If not, you might see little or no benefit. Imagine the world's worst library. We're talking a million books, completely unsorted. Just absolute chaos. Romance novels next to car repair manuals next to ancient philosophy texts. And somewhere in this mess is one specific book. Quantum Mechanics for Cats. Now, searching this library with a regular classical computer is like having one person walking down the aisles. Pick up a book, nope, not it. Put it back. Pick up another, nope. Put it back. Time. In the worst case scenario, that book is literally the last one checked. That's a million books examined. Exhausting. But here's where quantum computing absolutely breaks reality. With a quantum computer, it's like that searcher suddenly splits into a million ghost versions, and each ghost checks a different book at the exact same time. They all exist in this weird state called superposition, checking every possibility simultaneously, in parallel. Now here's the catch. There's no way to just ask all million ghost searchers what they found. The moment there's a measurement, the moment someone checks the result, all those parallel realities collapse into one answer. It's like Schrödinger's library search. Everything exists in possibility until observation happens. Let me give a concrete example. The rock star of quantum algorithms is Shor's algorithm. Imagine those library books are locked behind a password-protected door. The only way in is to crack the code. A classical computer would try every possible combination. 0001, 0002, 0003, all the way to 9999. For really long passwords, like the ones protecting bank accounts, this could take thousands of years. But Shor's algorithm uses superposition plus something called interference. Think of interference like sound waves. Sometimes waves amplify each other, sometimes they cancel each other out. Quantum algorithms choreograph all those parallel possibilities so that the wrong answers interfere with each other and cancel out, while the right answer gets amplified. It's like conducting an orchestra of realities. And with Shor's algorithm, encryption codes that would take classical computers millennia to break become solvable. Which, is why cybersecurity experts are freaking out right now. Then there's Grover's algorithm. Back to our messy library. Instead of checking all million books one by one, Grover's algorithm finds the target book in about 1,000 checks. Now that still sounds like a lot. But here's the thing, that's the square root of a million. Going from a million steps to 1,000 steps. For massive problems like searching enormous databases, that speedup is absolutely game-changing. So here's what quantum algorithms really are. They're carefully choreographed dances of possibilities. They use superposition to explore multiple paths at once, interference to amplify correct answers and cancel out wrong ones, and entanglement, where particles become weirdly connected across space, to solve problems in ways classical computers just fundamentally cannot match. So the real message is, quantum computing is not just faster hardware. It's different algorithms for different problem structures. When the structure fits, the speedup can be huge. When it doesn't, quantum doesn't help much. Alright, let me leave you with the key takeaways about quantum algorithms. First, quantum algorithms are not just faster versions of classical algorithms, they're fundamentally different beasts. Think of them as carefully choreographed dances of possibilities, where we're manipulating probability itself. Second, they work using 3 quantum superpowers. Superposition lets us explore multiple paths simultaneously, interference amplifies the right answers while canceling out the wrong ones, and entanglement creates those weird quantum connections that let qubits influence each other across space in ways classical bits simply cannot. Third, here's the critical point that gets lost in the hype. Quantum speedup only happens for specific problem structures. We're not talking about a faster processor. We're talking about a different computational paradigm that excels at certain types of problems. Factoring large numbers, searching unsorted databases, simulating quantum systems, optimization on specific landscapes. Fourth, for problems that don't match quantum structure, like loading your email, browsing the web, or most everyday computing tasks, quantum computers offer no advantage. They might even be slower. The structure of the problem has to fit the quantum approach. And finally, when someone says quantum computers are faster, the complete sentence should be, quantum computers are faster for certain problems where quantum properties can be exploited. That's not a limitation, that's precision. And for those specific problems like breaking encryption or discovering new materials, the speedup can be exponential and world-changing. The bottom line: quantum algorithms are a new tool in our computational toolbox, incredibly powerful when used for the right job, but not a magic wand for everything. That's all for today. Take care.